Hello learners, I am Dr. Nidhi Mathur and the subject expert of this episode is Dr. Neeti Mathur, teaching in National Law University, Jodhpur, Rajasthan. Previously, we discussed sensitivity analysis in operations research, which is widely used by businesses. Our topic of discussion for today is the duality theory. Let us begin with understanding the meaning of duality theory. The theory of duality is one of the most interesting techniques in operations research and important concept in linear programming. Every linear programming problem has a correlated linear program called its dual in such a way that a solution to a dual problem is provided by the solution of its original linear program. This is a basic idea behind the duality theory. The solution for two linear programming problems are obtained while a linear program is solved by simplex method. To understand advanced topics in linear and nonlinear programming, it is vital to understand the relation between a linear programming and its dual. The relation between linear programming and its dual provides us important understanding about many optimization problems and algorithms. It translates to interesting insights about economy and provides additional insights into sensitivity analysis, making this relation and the knowledge of duality of great importance. Maximizing revenue or profit depending on limited resources is the objective of linear programming problem, where it acts as a resource allocation model, and the associated dual problem provides interesting economic interpretations of this model. If we look at the problem from the standpoint, the important outcomes that can be derived in duality are the dual of the dual is primal. If one is a maximization problem, then the other is a minimization one. The necessary and sufficient condition for any LPP and its dual to have an optimal solution is that both must have feasible solution. Fundamental duality theorem states that if either the primal or dual problem has a finite problem solution, then the other problem also has a finite optimal solution, and also the optimal values of the objective function in both the problems are the same. That is, maximum z is equal to minimum z apostrophe. The solution of the other problem can be read from the z to c row below the columns of slack surplus variables. Existence theorem states that if either problem has an unbounded solution, then the other problem has no feasible solution. Complementary slackness theorem states that if a primal variable is positive, then the corresponding dual constraint is an equation at the optimum and vice versa. If a primal constraint is a strict inequality, then the corresponding dual variable is 0 at the optimum and vice versa. Let us now understand the different types of primal dual problem. There are three types of primal dual problems. These are symmetric. Here all constraints of both primal and dual problems are in equations and variables are non-negative. Unsymmetric. Here all constraints of primal are equations and primal variables are non-negative. Mixed type. Here some constraints of primal are equations and some variables are unrestricted in sign. Now that we have discussed the different types of primal dual problems, it is important that we concentrate on the concept of duality in linear programming. As discussed, while defining duality theory, it is clear that every linear programming problem has another linear programming problem related to it and thus can be derived from it. The actual linear programming problem is called primal and the derived linear problem is called dual. The optimal solution of dual provides complete information about optimal solution of primal and vice versa. It implies that both primal programming problem and dual programming problem is very closely related. Thus, the duality theorem is the one that concerns with relationship between the solutions of primal and dual linear programming problems. If either the primal or the dual has a finite optimal solution, then the other problem has a finite optimal solution and the optimal values of their objective functions are equal. This implies that the objective value of any feasible solution to the minimization problem is greater than or equal to the objective value of any feasible solution to the dual maximization problem, and it holds true for any pair of primal and dual linear programs. It suggests if one of the problem is feasible and unbounded, then the other problem is infeasible. This is one form of the duality theorem. Another form of theorem states that both the equations have finite optimal solutions with equal optimal values of their objective if both problems have feasible solutions. The original linear programming problem is to be formulated in its standard form before solving for the duality. In standard form, all the variables in the problem are non-negative and greater than equal to and lesser than equal to are signs used in the case of minimization and in the case of maximization. Expressing the primal problem in the equation form is required to define the dual problem, and with the format of the simplex starting tableau, this requirement is consistent. Thus, the result provided by the primal optimal solutions are applicable directly to the associated dual problem. The dual problem is constructed by defining the primal in equation form as follows. Maximize or minimize z is equal to sigma nj equal 1 cj xj, subject to sigma nj equal 1, aij xj equal bi, where I equal to 1, 2 and so on till m. x1 is greater than equal 0, j equal 1, 2 and so on till n. If any slack, surplus and artificial variables are present, they are included in the variable xj. J here is equal to 1, 2 and so on till n. The table A represents the construction of dual problem from the primal. Now, functionally we have the following points in check. For each primal equation, a dual variable is defined. For each primal variable, a dual constraint is defined. The left hand side of the dual constraint is defined by the constraint, that is column, coefficient of a primal variable, and the right hand side is defined by its objective coefficient. The right hand side of the primal constraint equations equals the objective coefficient of the dual. The rules for determining the sense of optimization, maximization or minimization, the type of the constraint, lesser than equal, greater than equal or equal, and the sign of the dual variables are summarized in table B. Note that the sense of optimization in the dual is always opposite to that of the primal. An easy way to remember the constraint type in the dual, that is lesser than equal or greater than equal, is that if the dual objective is minimization, that is pointing down, then the constraints are all of the type greater than equal, that is pointing up. The opposite is true when the dual objective is maximization. The first and second constraints are replaced by an equation. The general rule in this case is that an unrestricted primal variable always corresponds to an equality dual constraint. Conversely, a primal equation produces an unrestricted dual variable, as the first primal constraint demonstrates. The general conclusion here can be that the variables and constraints in the primal and dual problems are defined by the rules in table C. It is a good exercise to verify that these explicit rules are subsumed by the general rules in table B. Note that the table does not use the designation primal and dual. What matters here is the sense of optimization. If the primal is maximization, then the dual is minimization and vice versa. Let us consider an example for better understanding of the duality concept. Example: let us consider the following problem. Maximize z equal 50 x1 plus 30 x2 subject to 4 x1 plus 3 x2 is less than equal 100, 3 x1 plus 5 x2 is less than equal 150, x1 x2 is greater than equal 0. The above original linear programming problem has a following dual problem. Minimize g equal 100 y1 plus 150 y2 subject to 4 y1 plus 3 y1 greater than equal 50, 3 y1 plus 5 y2 greater than equal 30, y1 y2 greater than equal 0. While making the dual linear programming problem, the following considerations came into the existence. The primal or original linear programming problem is of the maximization type, while the dual program is of minimization type. The constraints values 100 and 150 of the primal problem have become the coefficient of dual variables y1 and y2 in the objective function of a dual problem. And while the coefficient of the variables in the objective function of a primal problem has become the constraint value in the dual problem. The first column in the constraint inequality of the primal problem has become the first row in a dual problem, and similarly the second column of constraint has become the second row in the dual problem. The directions of inequalities have also changed. That is, in the dual problem, the sign is the reverse of a primal problem, such that in the primal problem, the inequality sign was less than equal to, but in the dual problem, the sign of inequality becomes greater than equal to. Now, let us discuss weak duality. Theorem for weak duality: suppose that x is a feasible solution of the primal and y is a feasible solution of the dual. Then Ax less than equal b, y t a greater than equal c t, x greater than equal 0 and y greater than equal 0. It follows that y t Ax is greater than equal C T x and y t Ax is greater than equal y t b. Hence, C T x is less than equal B T y. This is the weak duality theorem which we state below. For any feasible solution x and y to primal and dual linear programs, C T x is less than equal B T y. The following theorem states one immediate implication of weak duality. Certificate of optimality: if x and y are feasible solutions of the primal and dual and C T x less than equal B T y, then x and y must be optimal solutions to the primal and dual. There is another interesting consequence of weak duality that relates infiniteness of profit cost in the primal dual with feasibility of the dual primal. As we now explain, let y be a feasible solution of the dual. By weak duality, we have C T x less than equal B T y for all feasible x. If the optimal profit in the primal is infinite, then infinite is less than equal B T y. This is not possible, so the dual cannot have a feasible solution. The following theorem captures this fact together with its converse, which can be established via a symmetric argument: infiniteness and feasibility in duality. If the optimal profit in the primal is infinite, then the dual must be infeasible. If the optimal cost in the dual is negative infinite, then the primal must be infeasible. Let us now discuss the strong duality. Theorem for strong duality asserts that if x and y are feasible solutions of the primal and dual and C T x equal B T y, then x and y must be optimal solutions of the primal and dual. This does not imply that there are feasible solutions x and y such that C T x equal B T y. However, the strong duality guarantees that the dual has an optimal solution if and only if the primal does. If x asterisk and y asterisk are optimal solutions to the primal and dual, then C T x asterisk equal B T y asterisk. Note that here and throughout, when we refer to an optimal solution, it is implicitly assumed to be finite. If the optimal value can get arbitrarily large, we say the objective is unbounded. There are two slightly different sorts of unboundedness we discussed, subtly different. In the first, the feasible region is unbounded, and in this situation, we say the problem is unbounded. In the second, the objective function can get arbitrarily large, and we say that the objective value is unbounded. Note that the second sort of unboundedness implies the first. It is time to understand some of the characteristics of dual problems. The major characteristics of duality in linear programming are: dual of the dual is primal. If either the primal of dual problem has a solution, then the other also has a solution and their optimum values are equal. If any of the two problems has only an infeasible solution, then the value of the objective function of the other is unbounded. The value of the objective function for any feasible solution of the primal is less than the value of the objective function for any feasible solution of the dual. If either the primal or the dual problem has an unbounded solution, then the solution to the other problem is infeasible. If the primal has a feasible solution, but the dual does not have, then the primal will not have a finite optimum solution and vice versa. The common method of duality is the dual simplex method. The dual simplex method is very similar to the regular simplex method. The only difference lies in the criteria used for selecting a variable to enter the basis and to leave the basis. In dual simplex method, we first select the variable to leave the basis and then the variable to enter the basis. This method yields an optimal solution to the given LPP in a finite number of steps, provided no basis is repeated. The dual simplex method is used to solve problems which start dual feasible, that is, whose primal is optimal but infeasible. In this method, the solution starts optimum but infeasible and remains infeasible until the true optimum is reached, at which the solution becomes feasible. The advantage of this method is avoiding the artificial variables introduced in the constraints along with the surplus variables, as all greater than equal constraints are converted into lesser than equal type. Let us now discuss the uses of dual problems. There are several different uses of dual problems. Understanding the dual problem leads to specialized algorithms for some important classes of linear programming problems. Examples include the transportation simplex method, the Hungarian algorithm for the assignment problem, and the network simplex method. Even column generation relies partly on duality. The dual can be helpful for sensitivity analysis. Changing the primal's right hand side constraint vector or adding a new constraint to it can make the original primal optimal solution infeasible. However, this only changes the objective function or adds a new variable to the dual respectively. So, the original dual optimal solution is still feasible and is usually not far from the new dual optimal solution. Sometimes finding an initial feasible solution to the dual is much easier than finding one for the primal. For example, if the primal is a minimization problem, the constraints are often of the form Ax greater than equal b, x greater than equal 0 for b greater than equal 0. The dual constraint would then likely be of the form a t y is less than equal c, y is greater than equal 0 for c greater than equal 0. The origin is feasible for the later problem, but not for the former. The dual variables give the shadow prices for the primal constraints. Suppose you have a profit maximization problem with a resource constraint I, then the value y underscore I of the corresponding dual variable in the optimal solution tells you that you get an increase of y underscore I in the maximum profit for each unit increase in the amount of resource I, absent degeneracy and for small increase in resources I. Sometimes the dual is just easier to solve. A problem with many constraints and few variables can be converted into one with few constraints and many variables. There are various advantages of application of duality theory. These advantages are: the duality theory yields a number of powerful theorems. Computational procedure can be considerably reduced by converting it into dual if the primal problem contains a large number of rows or constraints and a smaller number of columns or variables. Solution of the dual checks the accuracy of the primal solution for computational errors, gives additional information as to how the optimum solution changes as a result of the changes in the coefficients and the formulation of the problem. This is termed as sensitivity analysis. Indicates that fairly close relationship exists between linear programming duality. Economic interpretation of the dual helps the management in making future decisions. Thus, to conclude, it can be said that every linear programming problem has associated with it a dual linear programming problem, and there are number of very useful relationships between the original, that is primal problem, and its dual problem that enhance our ability to analyze the primal problem. For example, the economic interpretation of the dual problem gives shadow prices that measures the marginal value of the resources in the primal problem and provides an interpretation of the simplex method. Because the simplex method can be applied directly to either problem in order to solve both of them simultaneously. Considerable computational effort sometimes can be saved by dealing directly with the dual problem. Duality theory, including the dual simplex method for working with super optimal basic solutions, also plays a major role in sensitivity analysis. With this, we are through with the understanding of sensitivity analysis and duality theory of operations research as applicable on various businesses. So, that is all for today. Hope you have understood. We will